Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syafiq Najmi bin Husaini. Today I would like to present our group assignment. So for question 1, we have choose number 6, which is the question is modulo P has no proper non-trivial subgroup if P is a prime number. So for the proving, suppose H is subgroup of modulo P where P is a prime number and H is a proper non-trivial. By following theorem 6.6, which is said a subgroup of a cyclic group is a cyclic. Therefore, H is cyclic because H is a subgroup of modulo P, which is modulo P is a cyclic group. Then, H equals to generated by B for some B in modulo P. By theorem 6.15, let G be a cyclic group with n element and generated by A. Let C element G and let C equals to A to the power of S. Then C generates a cyclic subgroup H of G contain n over D elements, where D is the greater common divisor of n and S. Also, subgroup generated by A to the power of S equals to B to the power of T. If and only if GCD Sn equals to GCD Tn. So, H contain P over D element where D is a GCD PB. D can only be P or 1 since P is a prime number. Then, if D equals to P, P over P equals to 1. Hence, H contain one element which is identity element and H would be the trivial subgroup of modulo P by the definition of the trivial subgroup. If D equals to 1, then P over 1 equals to P. Hence, H has P element, which would be improper subgroup of modulo P by the definition of the improper subgroup. This contradicts our assumption of P being a prime number. Therefore, modulo P has no proper non-trivial subgroup. So, we proceed to the example of theorem 6.15. The question is find all order of subgroup of modulo 20. The solution is this is an additive group with a generator A equals to 1, with S equals to 2, B equals to A to the power of S, which is equals to 2, and 2 generates a subgroup of order n over D where D equals to GCD 22, which is equals to 2. So, n over D equals to 20 over 2, which is equals to 10. With S equals to 4, the generates by 4 has order n over D, which is equals to 20 over 4, which is equals to 5 element. With S equals to 5, the generates 5 has order n over D equals to 20 over 5, which is equals to 4. With S equals to 10, generate by 10 has order n over D equals to 20 over 10, which is equals to 2. Next, for S element of set 3, 7, 9, 11, 13, 17, 19, D equals to GCD and S equals to 1 and n over D equals to 20. Each of these generate modulo 20. In totally, we get subgroup order for 1 generator is equals to 0. For order 2, the generator is 10. For order 4, the generator is 5 and 15. For order 5, the generator is 4, 8, 12 and 16. For order 10, the generator is 2, 6, 14, 18. For order 20, the generator is 1, 3, 7, 9, 11, 13, 17 and 19.
Now, I will be presenting question number 2. We chose theorem 22.8. Theorem 22.8. Theorem 22.8 stated that if R is a ring with additive identity 0, then for any A, B is an element of R, we have the first property, that is 0, 0 A equals to A0 equals to 0. The second property, A times negative B equals to negative A times B equals to negative A times B. The last property is negative A times negative B equals to A times B. So, let's look into property number 1. To prove property number 1, note that by axioms R1 and R2, A0 plus A0 equals to A bracket 0 plus 0 close bracket equals to A times 0 equals to 0 plus A times 0. Then, by the cancellation law for the additive group R positive, we have A0 equals to 0. Likewise, 0A plus 0A equals to bracket 0 plus 0 times A equals to 0 times A equals to 0 plus 0A. Implies that 0 times A equals to 0. This proves property number 1. Next, we move to property number 2. In order to prove property number 2, we must remember that by the definition, negative A times B is the element that when added to A times B gives us 0. Thus, to show that A times negative B is equals to negative bracket A times B, we must show precisely that A times negative B plus A times B is equals to 0 by the left distributive law. A times negative B plus A times B is equals to A bracket negative B plus B is equals to A times 0 is equals to 0, since A times 0 is equals to 0 by property 1. Likewise, negative A times B plus A times B is equals to bracket negative A plus A bracket times B is equals to 0 times B is equals to 0. For the last property, property 3, note that negative A times negative B is equals to negative bracket A bracket negative B by property 2. Again, by property 2, negative A bracket negative B is equals to negative bracket A times B, and negative bracket A times B is the element that when added to negative bracket A times B give us 0. This is A times B by definition of negative bracket A times B and by the uniqueness of an inverse in a group. Thus, negative A times negative B is equals to AB. Based on high school algebra, it seems natural to begin a proof of property 2 in theorem 22.8 by writing negative A times B is equals to negative 1 times A times B. In exercise 30, we will be asked to find an error in a proof of this sort. It is important that we understand the preceding proof. The theorem allows us to use our usual rules for signs. For the example question for theorem 22.8, what is wrong with the following attempt at a proof of property 2 in theorem 22.8? Negative A times B is equals to negative 1 times A times B and is equal to negative 1 times A times B and is equal to negative A times B. And our answer is negative A times B is equals to negative 1 times A times B and is equal to negative 1 times A times B and is equal to negative A times B. In the above procedure, negative A is not equal to negative 1 times A because negative 1 may not belongs to the ring R, so the remaining procedure are invalid. That is the end of our presentation. Thank you, sir.